The second structural isomerism is called linkage isomerism. In this, as the name suggests, the isomers differs in the linkages formed by the ambident ligands. Let us take the example. This is pentaamine nitrito. We will call it N-nitrito because it is attached to the same metal ion through N. Cobalt 3 chloride. Now, we can have another isomer with the same formula in which we can have all nitrito are forming bond through the oxygen, and they are bonded to the cobalt through this oxygen. And chlorido is like this. We can draw the structure of such isomers like this. So you can see in the first structure, there are 5 amine, it's fine. The sixth ligand, nitro, is attached to the cobalt through N, whereas this is the second type of the same compounds isomer is possible, in which what we find is that the nitro group is attached to the cobalt through oxygen. So these two are linkage isomers because NO2 ligand is an ambident ligand, and we will call this isomer as pentaamine O nitrito cobalt 3 chloride. So this is how we can name them by putting up a capital N or capital O to differentiate which nitrito we are having. This is pentaamine O nitrito, this is N nitrito. So, and these are the structures, and this is by circling it we can easily differentiate that, and we can show how the linkage ambident ligands are forming different linkages with the metal ion. Now let us move to the third type of isomerism, which is called hydrate or solvate isomerism. It is the type of isomerism in which, as the name suggests, the isomers differs in the number of water molecules present as water of crystallization. Yes, the number of water of crystallization will be different in the different isomers. Like we can take example of this is hexaaqua titanium 3 chloride, and this is what we can call as anhydrous because it's not having any water molecule present as water of crystallization. Now what we can do is we can put a chloride inside and we can put water out, one molecule of water out, as the total number of ligands has to be 6. The primary valence, the secondary valency of the metal ion is kept same. So what we can do is we can put one chloride inside like this. So there are 2 chloride left out and 1 water is coming out of this. Now this is called monohydrate. This is pentaaqua chlorido titanium 3 chloride monohydrate. Whereas we can do one more replacement of this one like this. So it's called dihydrate. Tetraaqua dichlorido titanium 3 chloride dihydrate. So all these three are the hydrate isomers or solvate isomers of each other, because these isomers differs on the number of water molecules present as water of crystallization in these isomers. Now let us see the fourth type of isomerism, which is called coordinate or coordination isomerism. Coordination isomerism. In this, both the cation and the anion of the coordination compound are coordination entities, and the isomers differs due to the exchange of ligands between the two metal ions present in the two coordination entities. Let me give you an example of this. Like let us take, we have this compound. In this, the first coordination entity is a cation, the second one is an anion. In this metal ion is cobalt, ligands are ammonia, and in the second ion, the second coordination entity, the metal ion is your Fe, and cyanido are your ligands. Now in this cobalt and the iron both are present in +2 states. So we have a +2 charge here, so -2 accordingly here. So iron, that is why, is in +2 state, which stabilizes everything. Now what we have to remember now in this case is that we can call this name of this compound will be tetraamine cobalt through to cobalt 2. We'll leave a gap because that's the name of the cation. Then we will start with tetracyanidopherrate 2. Now in this case what we can do is we can have another coordination compound with the same molecular formula, in which what we will find is that the ligands will exchange their metal ions. Like cyanido will go to the cobalt and the amine will go to the Fe. So in that case what we find is the next isomer we can draw out of this will be this one. So yes, these two are coordinate isomers. Now on seeing this we can say that, oh, in this the metal ions have exchanged their position, not the ligands. Then why we were saying that the ligands exchange their position with the metal ions? Yes, ligands exchanges. But the problem comes is the moment the cyanido comes forms a coordination entity with cobalt, that coordination entity becomes anion, so it has to be written later afterwards after the cation. And the moment the Fe gets this ammonia, its coordination entity becomes cation, so it is to be written first. So actually it is only the ligands which are exchanging the position, but since their charges gets changed of the coordination entities, it looks as if that the metal ions are exchanging their position. So these two are the coordination isomers of each other, and we can call this as tetraamine iron 2, leave a gap, and then start tetracyanidо cobaltate 2. So this is what is your structural isomerism is. Stereoisomerism. The second type of isomerism shown by the coordination compounds is stereoisomerism. Now we know what is stereoisomerism. It is the isomerism in which the isomers have even the same structural formula, but they differ in the three-dimensional or spatial arrangement of the ligands around the central metal ion. So the three-dimensional arrangement of the ligands will be different in the isomers, otherwise their basic structure will also be same. Now stereoisomerism we know is of two types. It is geometrical, and second category of this is optical. So now let us first see the geometrical isomerism, stereoisomerism. Now the most important thing before to start this is then you need to understand, basically in our syllabus we have mainly the coordination entities of the formula ML6 or ML4. The 6 will be your octahedral coordination entities. ML4 can be of two types. It can be your square planar or it can be your tetrahedral. But the other fact about this is the ML4 type 1 is that we have very few examples of tetrahedral coordination entities, and that too most important to note is that all tetrahedral molecular coordination entities, what we find is they doesn't show stereoisomerism, because it becomes very difficult to differentiate that or to find out that which two ligands are opposite to each other, so we won't be able to assign them as cis and trans type of isomerism, and they always contains one or the more elements of symmetry, so that is why they doesn't show optical. So we have only, that is why what we need to know is we have only the square planar or the octahedral coordination and complexes showing stereoisomerism. Now let us first see the geometrical isomerism in square planar complexes. In square planar complexes, the complexes with formula Ma2B2, where A and B are both unidentate ligands, shows cis-trans isomerism. That means out of the four, two ligands has to be of one type and the other two ligands has to be of the other type. So what we can put is, it is like this. This is the best example to show this. This is called diamine dichloridoplatinum 2. Now in this what we can have is one isomer in which the same type of ligands are on the same side, it's like this. Now this one is called cis isomer, and the other type is like this, which is called trans. The same type of ligands are opposite to each other. So when they are opposite, it's called trans. When they're the same side, it's called cis. So this is how we have two isomers of this compound, the two isomers of this stereoisomers of this compound, or this formula. And this cis compound is very special because this is called cisplatin, which is used in the chemotherapy. So this is what we have: square planar stereoisomerism, specifically geometrical cis trans isomerism in square planar complexes.